The next of our four ideal topologies is our shunt series, or our current amplifier topology. So if we look at this first diagram here, we can see we have our input current to be amplified over here on the left, which is coming into this block amplifier AI, and is also connected to this feedback block beta I, and these connections are done in parallel. So sort of our input from our feedback from beta I is coming back and being added in parallel, so that's where we get the shunt or parallel for the first side. And then on our output, we notice we have I naught over here on the right going through this load resistor RL, and we notice that our AI and our beta I blocks are connected in series. So that's where the name shunt series comes from. So just like we did with our voltage amplifier, we can sort of expand this a little bit. So if we're looking at our basic amplifier block here, our AI, we can approximate that with this here, where we have an input resistance Ri, and then on the output side we have a dependent current source which is in parallel with some output resistance R naught. Same thing with our beta I, our feedback block. So up here we have our feedback block, and down here, if we're considering an ideal feedback block, if we don't want to consider loading, what we do is we say we have Ri equals 0 for this feedback loop. So let's just add that note here. So we're assuming that we have Ri equals 0 for our feedback loop. And so again, that's just so we're kind of neglecting loading effects of this feedback loop, and we're considering an ideal case. Okay, so the first thing we're going to want to do, just like we did for our voltage amplifier, is analyze this in order to figure out our transfer function. And then in later videos, we're going to come back and talk about our input resistance, our output resistance, and ultimately an equivalent circuit for this current amplifier. Okay, so let's start out looking at our output current on the right. So we notice that our output here has been short-circuited. So I basically just come from these two output nodes and connected them together with a short circuit. And so what that means is any current from this dependent source here is going to go through this path and become our I naught, and we're not going to have any current here. So this is going to be 0 because, again, current is going to take the path of least resistance. So in that case, we can say our I out is going to be equal to AI times I epsilon, or our error current. Okay, and so now let's shift our attention back to our input side. So of course the two are related through this feedback loop, which is circled in red. So in that feedback loop, we can see that that feedback current, I sub FB, is equal to beta sub I times I naught times our output current. And so just like with our voltage, we had a slightly different beta value, so same thing here. So this is our feedback current transfer function. So same basic idea as our feedback transfer function, except now we're saying it's specific just to current. So feedback current transfer function. Okay, so we can also look at the relation between this feedback current and our input by looking at a Kcl equation at this node here. So we see, and so I've forgotten to label this, but we have some Rs. But for our initial sort of derivation here, we're going to assume this Rs is 0, such that we're going to have In coming in this way. And so not 0, sorry, we're assuming that this is infinite. So let me fix that. So we're assuming that our Rs is approximately infinite, such that we neglect it, and we have our input current coming this way, and then splitting into two parts, our feedback current and our error current. So we can say then our input current is equal to our error current plus our feedback current. And so again, that's because we're neglecting our Rs. And so that's just to make this initial analysis easier, and then we can of course account for that later. Okay, so now what we want to do is sort of combine all of these equations and see if we can't figure out our transfer function equation. So where we can start is we can say, well, our error current is equal to our input current minus our feedback current, so just sort of rearranging that last Kcl equation. And then we can say, well, we know that our feedback current is really just beta I times our output current. So if we want a transfer function, of course our goal is to get it in terms of just input and output current. Okay, well, so now what we can say is we know from our very first equation that our output current is equal to AI times I epsilon. So AI, and then what we're going to do is we're going to substitute all of this in for our error current, I epsilon. So we get I input minus beta I output. And so if we rearrange that, we can solve for our closed loop current gain, A sub IF, which is defined as the output current divided by our input current. And we find that that is equal to A sub I divided by 1 plus beta I times A sub I. And so I didn't mention explicitly earlier, but of course A sub I is just the open loop gain of this ideal amplifier A sub I up here in the top. And so this A sub IF, again, is our closed loop current gain. Okay, so we found our transfer function. So like I've said, in later videos, we're going to come back and we're going to look at how to find our input and our output resistance.